Hey, welcome back, students. Hey, what we want to go ahead and do today is we want to go ahead and review a little bit of the gas laws. And so if we go ahead and look at this, we're going to go ahead and begin with the first law. Now, we've already explored Boyles Law, and what we learned from Boyles Law is that it follows the following equation. We know that it involves pressure and it involves volume. And so according to Boyles Law, we're going to see that the pressure and the volume are inversely proportional. And what this means is that as the pressure increases, the volume is going to decrease. And if the volume increases, pressure will also decrease. And so this equation is very important to us, especially when we only have two variables. So this equation is often used to solve those kinds of problems that only have variables that include pressure and volume. And when you're looking at solving these types of problems, what you want to do is look for keywords such as initial pressure or initial volume. Essentially, that's going to be your P1 and your V1. And the other item is look for words like resultant or final volume or pressure, because that's going to be your V2 or your P2. A second equation that we looked at before was Charles' Law. And so this equation here is going to be written as follows. You're going to get the volume divided by the temperature in the first instance, and V2 divided by T2 in the second instance. Now, according to Charles' Law, the volume and the temperature are proportional to one another directly. And so what this means is if you increase temperature, that means that the volume is going to increase. And if the volume increases, that means that the temperature must have increased, because if we remember what we learned about the kinetic molecular theory, we learned that molecules are going to be moving pretty fast, especially if you increase its temperature. And as a result of moving so fast, they're going to create more collisions with the barrier of whatever surface or container they're in, causing the volume to increase. If we have this particular equation in our possession, what we're trying to figure out here is when we're trying to solve problems, we're going to be using this equation, V1 divided by T1 equals V2 divided by T2, especially when we're dealing with equations or problems that have only two variables, temperature and volume. And again, like the other one, Boyles Law, we want to look for keywords such as initial temperature or volume, or resultant temperature and resultant volume. The next equation that we're going to go ahead and look at is going to be Gay-Lussac's law. And in this particular law, what we've got here is we've got a equation that involves two variables, pressure and temperature, and it looks like this. Pressure divided by temperature is going to be equal to constant K. Now, this constant is something that we calculate ourselves. And so we calculate it by taking the pressure and dividing it by the temperature. Now, according to the Gay-Lussac's law, we know that pressure and temperature are going to be directly proportional. Again, like the previous equations, particularly Charles' law, if we increase the temperature, this is also going to cause an increase in the pressure, and vice versa. So if we have an increase in pressure, this will be a direct result because the temperature increased. Now, this equation is going to be used when you're trying to solve problems that only contain one pressure variable and one temperature variable. And typically what we're going to try to do is try to solve a constant. So maybe I ask you, if you have this pressure and you have this temperature, what would be the constant for this equation, according to Gay-Lussac? Okay, and so this constant then is something that we solve for, and we figure this out by dividing the pressure divided by the temperature. Now, another new equation that we're going to be looking at today is going to be Avogadro's law. Now, Avogadro's law essentially deals with volume and number of moles. Now, we recall from previous discussions, Avogadro was very instrumental in allowing us to understand that 1 mole of a substance contained a certain number of particles, and that was 6.02 times 10 to the 23rd. And so here's the actual equation that we're going to use. It's the very top corner. And according to Avogadro, the law essentially proposes the following, that the number of moles of a gas is directly proportional to its volume. In other words, as the number of moles of a gas increases, so is the volume, simply because you have more particles available. And that makes sense. It's kind of like taking a room, for example, and the more people you put into the room, so assuming you can bend the walls of this room, if I put in a certain amount of people and I fill up the room, then we're at capacity, it's full. But if I continue to add more and more and more, essentially it's going to start stretching the walls. Kind of like what happens when you overstuff a suitcase. you can't really close it down, because if you've got clothes overflowing on the edges. Well, it works the same way here with the molecules in the gas. Now, the equation is used to solve problems that have variables of volume and moles. Now, keep in mind that moles is identified as a N in the equation, so we're looking at N as the number of moles. And we also want to make sure that when you're solving these types of problems, you're looking at keywords such as initial moles or volume or resultant moles in volume. Okay? Now, these are the actual four equations that we have, and we're going to use these four equations to go ahead and derive the another equation that we call the combined gas law. And the combined gas law is going to be derived essentially by taking the Boyles Law, Charles Law, Gay-Lussac's Law, and Avogadro's Law and combining them all together. Let me